Hey, John here. Let's talk about how to interface an asynchronous bus to synchronous circuitry inside of an FPGA. A big thanks to the supporters of my channel, especially those VIP Patreons listed here. A big thank you. Thank you very much. The code that you're going to see today is on a GitHub website. It looks like this, and I'll put a link to this below the video in the description on YouTube so you can find it easily. I'm in this subdirectory here called FPGA, and in particular we're looking at Nouveau 2. Don't worry about the fact that this is for a Z80 and so on. I'm very specifically going to talk about the test benches and cases around these finite state machines that I'm going to use as special synchronizers that are not really metastable style synchronizers, okay? So don't confuse that. And this is the whole point of today, is this specialized synchronizer that I'm going to use so that the FPGA can recognize one of these edges from the phi clock that's running during an I/O operation and or a memory operation, or a bus transaction, we should say, right? So the key here to observe is that this CPU, the Z8S180 in particular, is running asynchronously, and what it expects you to do is, for example, if it's issuing a read cycle like this right here, it will assert a memory request signal, which is this one right here. It'll go low. It's active low from the processor, and read at the same time. So you basically put these through an OR gate, and whenever that OR gate is true, you've got MREC and read are both active at the same time, which means I want to read from the memory at the address that's in the address bus that is shown up here. The timing constraints are such that the address bus is guaranteed to be stable prior to the falling edge of the read and MREC signals, and will continue to be stable after a certain hold time after these things go high. At the end of this cycle, MREC and read both go high as a result of a falling edge on T3, as shown here with this distance here, how many nanos after this. If you look at these up in the timing tables, the 12 and the 13, these are 25 nanos each, which means that this could go high along with the rising edge of T1 in the worst case. Over here, you've got 8 and 9 from the falling edge of T1 here, showing that these will go low no later than however long these timing constraint numbers are from the falling edge of T1. So let's look really quick. I got 8, 9, 12, and 13. In the table above is where you get these timing numbers from. Well, we got 8, 9, 12, and 13. Almost all these are 25 nano, 25 nano, 25 nano, 25 nano. Okay, let me get back to where we were. So what that means is, in the worst case scenario, is that this wait state is optional, and I have it disabled on this processor if you're not really following the channel. If you are, this is, the memory I turned off the wait states. You cannot turn off a wait state during an I/O cycle on this particular processor. This will all become a little more important as we go, because I have to pick which edge I want to use when I'm transferring data into or out of the CPU. Now down here it shows you the relationship between these, the falling edge and the leading edge of these memory bus and the I/O bus request boundaries here. The tenure of this bus transaction. And much like the address bus, up here it says the address will be valid before the I/O goes valid, and it'll stay for a hold time afterwards, and so on. Just like it does for a memory transaction. Down here it says, look, if I'm reading from the data bus, the FPGA in this scenario, the peripheral device, better have its data ready. This is not nanos. I keep throwing that out there. Number 15, timing constraint 15 before this line here, which is the rising edge of T3. I don't see a plus mark. It probably needs to be one right there. It's very annoying when they make a mistake in a diagram like this, especially during a transcription when somebody decides it doesn't matter, and it does because I'm an engineer and I'm anal retentive about these things. Anyway, so what we need to do is say I need to guarantee the data in on a memory read is valid that much before rising edge of T3. So let's see what was, oh, no, I forgot what I'm yakking. I can't remember these numbers. Number 15. Oh, I got a 15. Who's got a 15? Yeah, 15, right there. Setup time, 10 nanos. That's not a problem for an FPGA. That's an eternity, even for a simple cheapie like the one I'm using. So I got to have my data on the line, 10 nanos before rising edge of T3. And since I'm running this at not even 20 megahertz, but if it was, this would be 25 nanos per 180 degree phase. This whole thing is 50 nanos long. So if, for example, the data became valid in my design on a falling edge here, actually this doesn't exist, this is a wait state, on the falling edge in this example of T2, I would have 25 nanos to get the data on there before the rising edge of T3, minus the 10 that I'm supposed to use for the setup time that I am responsible for, which means as long as I got 15 nanos after the falling edge of T2 to waste, as long as I get the data on there before then, I'm good for that setup time. The hold time is what? We'll see in the design that my hold time, I'll keep the data on there until this rising edge goes out, and the sample that the CPU uses is on the falling edge of T3, and these are all 25 nano worst case after T3 anyway, which means it's at least 0 or if not more. So as long as I'm on there that long, we're good. Okay, now if I have to read data from the Z80, if the Z80 is writing to me, or my CPU writes to me, it will make sure that the data is valid prior to the write signal going active. And this diagram has obviously been transcribed by a dumb fool, and they didn't bother to show you what a write looks like to memory because they got obsessed with the opcode fetch. There should actually be a formal memory write cycle in here, but it turns out it's exact same as this, minus the wait state, and it might even say that down here. Memory read, write, same as I/O, except there's no automatic wait state. Okay, so that covers it, but come on, people. How hard is it? Okay, very good. Anyway, the point is the data out is valid before the falling edge of write for whatever the 24 is, and almost everything in that diagram above was 25 nanos. I'm sure they'll give us the courtesy of having the data ready by then. I wouldn't be surprised if it's almost 0. 24, number 24. What do you got, 24? Who's got 24? Going once, going twice. Oh, look, they give me 10 nano. I got to give them 25. Well, the setup time on the data here was 10 as well. All right, so we're even Steven on that one. Point is, the data out is valid prior to the falling edge of write, and it'll hold after the rising edge of write ends over there. An I/O cycle at a minimum is this long. It can be longer if you add more wait states, which I have all that shut off in this configuration. So now that we got the lay of the land here, what do we got to do? I'm mostly obsessed right now about I/O cycles. I also have a memory cycle that I'm going to do in there, but that will go out in the wash because I'm going to do all these the same way. And I'm going to do this. I'm going to target this, okay? When these go low and the clock is going around, phi is the master clock at the CPU, and it provides that back to the FPGA. And I've got that as an input in my FPGA design. So I've got this clock, and I'm going to use this as the clock for my logic that's going to come up with a variation of this signal here that's synchronized to phi, and it will go active for one clock period. All right? So the goal here is to take this asynchronous signal, turn it into a synchronous signal that's phase aligned to phi here, such that one and only one active going edge on phi will appear in an enable window that I can use to gate latches and memories and things like that for I/O devices and memory and whatnot. Now, In the past, if you've been following my channel, the code we're going to look at, I've been cheating, and I'll continue to do that to some degree. When transferring data out of memory, for example, what I do is I enable the memory device and just let free run and many edges go by while the memory is enabled. And I'm cheating because, I really should only have one edge in there, but it's memory and no one else is looking. And if I say I want to read the memory and I clock it, 1, 2, 3 times. Read. And the Verilog is designed to continuously read values out of the memory inside the chip. Does it really matter? I'm going to get the same value 3 times in a row, and all will be well. That's why I didn't bother synchronizing it to only one cycle. Same can be true for I/O devices, and I actually do that in an older version of my code as well. However, if we were to create an I/O device and we want the I/O device to have some knowledge, like a self-resetting flag in a register that says once you've read it, the flag will reset itself. Now we have a new problem. We have to make sure that one and only one active going edge will go by during this bus tenure, so that when I read the value, and I reset the status bit that's self-clearing, I don't then try to read it again and see the cleared one, okay? All right. So this is one example of why this is important to do. Sometimes it's important, sometimes it's not, okay? It's not when you're reading and writing to regular old static RAM, because who cares if you write the same value in there twice? You're probably wasting some power. I get that. But, the simplification of the design when it doesn't matter, it can say quite a lot, especially in the hobbyist community. Not making things unnecessarily complex is a great feature. On the other hand, like I said, sometimes you do care, and we have to be very careful. Now, sometimes you don't have enough clock edges in here to put a regular old Verilog, HDL synchronizer circuit, which is a shift register, that are normally used to deal with metastability problems. In this case, we don't necessarily have to worry about metastability because the things I'm going to use as inputs in my circuit design already are guaranteed to have a setup and a hold time around the edges that I'm looking at in here. Okay, so I want to make sure it's perfectly clear to anyone watching this. This is not a synchronizer to solve any metastability problems. Okay, just so we're 100% clear. This is a synchronizer. Maybe it's got a better name. I look forward to your comments below on YouTube. Seriously, if there's a formal name for what I'm talking about, great. Let me know. I will start using it. But this is going to take this signal here, and it's going to basically compress it so that it'll go true, it'll become true somewhere in here and then go false over here. And for example, if I'm reading from my I/O device, what I really want to do is try to get the data onto the data bus as soon as I can, as long as it's out there. This is 10 nanoseconds, remember, before the falling edge of T3, I'm good. I'm better if it's out there by the time the falling edge of TW or even the falling edge of T2 comes along. The earlier I can get the data out there, the longer the FPGA has to drive that data bus and to overcome any, parasitic capacitance and things like that may cause a really low slew rate. The rise time on the signal or fall time on the signal might take a long time, because this is the time after it is stable. Okay, if you look in the spec, these little plus marks are like 80% or 70% of the way to where it's got to go. Okay, it's not over here. It's done slewing to its voltage. Okay, is the way I want to think about it. So that's the worst case scenario. In my mind, in other words, my words are, I'm moving this all the way out to here. Okay, making sure that I'm ready so early that I can't have a problem. Okay, so that's how you want to think about when the CPU reads from the FPGA. I've got a signal that goes low on IO rec and read, And these are all 25 nano from the falling edge of T1, the worst case scenario, which means these might go active on the rising edge of T2. Could be that long before these go active. So what I want to do is find a way, in my opinion, to isolate this falling edge of this clock. So in a simple kind of minded thing, what I'm going to do is I'm going to say I want to create a signal that goes low or becomes active, because I'm going to use positive logic inside the FPGA so I don't have all this upside down junk to think about in my source code. I want IOREC. I'm going to have like an IOREC underscore read or something like that. And it'll go active when these two are both true, which could happen as late as the rising edge of T2. Then what I want to do is I want to stay active until I see the first falling edge, which will be the falling edge of T2 right there. Then I want it to go false again. So what I want to do is I want to use this falling edge. I'm going to have a Verilog always block with like a neg edge on phi, and inside there I'm going to say if this IOREC read signal that I'm going to invent is true, then and only then do I want to do what I want to do, which is to do the transfer of data out of or into the latch that's going to hold the read data that I'm going to then send to the CPU. Now, I'll do a very similar thing with writing, but where writing is concerned, I want to write it as late as possible, but not too late, because the CPU is sending me the data in that scenario, and it may not be stable on the bus, even though they're going to put it out over here. Again, it might quiver around and ring a little bit before it stabilizes, so I want to consume it as late as I can. Optimally, what I'd like to do is consume it on the falling edge of T3. But I want to reuse my design. We'll see in a minute that what I'm going to do is I'm going to aim for the falling edge of TW during an I/O cycle, because that turns out to be the falling edge of T3 when there is no wait state during a memory transfer. So to recap here, I want to read from the FPGA. The FPGA needs to latch its output data, or at least acknowledge that a read has taken place on this falling edge at the end of T2. And when there's a write operation, the FPGA should consume the data from the CPU on the falling edge of TW. And it should do it once and only once in each situation, so that if a I/O device peripheral would do something along the lines of every time data is written into the device, it might advance a counter. As it consumes data from the CPU, for example, it may do this over and over again, accepting 1 byte per transfer and storing it in the FPGA or in the peripheral in some way into a set of registers, which is what you have in Z80 peripherals all the time. You've this out-IR, or the OTR instruction, which is a repeated output instruction, which continuously writes bytes to the same I/O port address. And that's why you need one and only one edge so that you can advance your counter. If you do this sloppily and you just say, okay, enable the I/O device, and you got edge, 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 you got 3 of them going here. Okay? Now, if you don't do this synchronously at all, and you do it asynchronously, and you just latch on the rising edge of these, it would work. However, if you use this rising edge, you don't know whether it happens almost immediately after T3 or way over here on the rising edge of T1, which gives you a fair amount of variation inside your design of the circuitry inside your FPGA. And what you really want to do is you say, I'm bringing it in at a very known point in time on a very specific edge of the main clock that synchronizes everything that's going on inside the FPGA, which is the fundamental basis of all, synchronous design, okay? So let's find the edge we care about and make it happen during that point in time. All right, so this is my Project Nouveau, a variation of that. I copied the files from some months ago when I did a video on how to hook up a Z8 S180 to the FPGA and boot up and run CPM. And what I've done is I modified the top level file, and I've added these finite state machine files, and I've got these test benches in here. So the easiest one to understand, in my opinion, is the write. These two slight variations of what's going on here. This one's a bit more straightforward. So let's start with this one and see what's going on. Here's how this thing works. I've got a couple of signals, obviously phi, I got a reset. This is really only useful for testing. Otherwise, it can free run and never be reset, and it will work, which is more akin to what happens in reality. But this reset presumably would be the same reset that you could tie to the CPU and stuff like that. And all I do there is reset the state to its idle state. IO rec is the IO rec signal from the CPU, but it's in positive logic form. Okay? Write is from the CPU in positive logic, high when it's true. Write tick is going to be my 1 cycle long write signal. It's going to be a lot like this IO rec, but as I said before, it's only going to last for 1 period of phi. Okay? Now, what do we got? This is usual state machine. I got a 2-bit state register when there's a neg edge on phi. So I'm using the negative going edge. You could use either one, but it turns out if you use the negative going edge, you get a slight benefit for the writing situation, because write goes active after the rising edge of T2, which means that I'm sampling on the falling edge here. When I sample on the falling edge of T1, write will be false. When I sample on the falling edge of T2, write will be true. Okay? And remember, my goal is to accept the write transaction on the falling edge of TW. So what I can do is when IO rec and write together are both true, I wait for a falling edge, and on this falling edge, I assert my tick signal. After the next falling edge, specifically after the next falling edge, I deassert my tick signal, and then I keep it low until the next transaction. So what I'm going to do is I'm going to identify this cycle right here, which is a wait state for an IO operation, but it's T3 if I'm writing to memory, because that doesn't exist and it's the same number of edges, okay? So that's what I want to do. So what I'm going to say here is I'm going to say the state reg is always 0 until I see the IO rec and write signals both true at the same time. Get this thing out of the way, which happens right here. Worst case, it happens coincident with the rising edge of T2. Normally, it'll happen right over here, okay? But it won't happen too close to this falling edge to fail to meet our setup time over here, which is the key. So that's going to be true. I'm going to set state next equal to 1 when that happens. So the next falling edge of phi comes along, and it loads the state register with the next state, and it gets a 1 put in there. So that will be right here. My state becomes 1 at this exact point in time. When I'm in state 1, I then continue to look at IO rec and read, and if it stays true, which it will for a little while, I say move on to state number 2. So it becomes true right here. It stays true for a while. Here's my write down here in my IO rec. Stays true, and I move on to state number 2 on the next falling edge right here. Okay? In state number 2, if it's still true, I stay in state 2 forever. That's all I'm doing here. And I say this write tick signal is true whenever I'm in state number 1. As remember that state number 1 is the state that is entered on the falling after, as a result of falling edge of T2, and I leave state 1 over here on the falling edge of TW. So as long as I'm in state 1, I should have a signal that goes high, then goes low after this falling edge, so that this falling edge can be used in another always block like this. I can say neg edge phi, and then I can say if my write tick is true, I can do my one time one edge protected operation right there, okay? So that's how this thing works. I have a test case. I don't think we need to look too much at this other than to note that I have one, and I've got some delays in here. I reset it, I wait a while, and I play around with some various signals in here. And the reason we don't need to go into that, I'll leave that as a task for the viewer. I don't want to waste your time looking at it, because when we run it, we'll see it in the waveform diagram anyway, and you'll see what it's supposed to do if I compile it. What do we IO rec write. We'll compile it and then open up the plot image. We don't have any errors from down here. Okay, so here's the plot. Here, I want to look at this signal. Oops, I only need to look at it once. This T1 is a signal that I generate synthetically in my test case, and I set it true during T1 of the sequence of phi clocks, so I can find it. All right, that's just you know, a cue, so I can figure out what's going on. All right. So what do I want to do? I want to see the phi. I'm gonna organize these and sort them out. First, let's put it all on the screen. Where's the? There we go. Zoom out. What am I doing? That was reload, not zoom out. Here it is. There we go. It's resetting and getting things going over here. All right. So I get the reset out of the way. There's the state junk. Here's the write signal. We got IO rec and write. Remember, these are the inputs to this thing. I'm going to go ahead and turn on the wave highlight, which does that. And then I'm going to look at my write tick coming out. Okay, as you can sort of see here, IO rec and write. This looks a lot like it does in the diagram, except for they're both active high, true, instead of low. These pulses up here represent the point in time when T1 from the CPU is taking place. All right, so this right there is the T1. There's T2. There's T wait, and there's T3 of an IO operation. All right, so in this scenario here, what have I done here? I've inserted IO rec true after the falling edge of T1, which is the earliest time that IO rec will ever go low. The latest time it'll go become active, I should say. The latest it'll ever do it is on this rising edge over here, which is the scenario I got. The next one over there, okay? So this one is what happens if this thing goes low super early. And I also have a scenario in here. What happens if write goes high super late? In fact, this is so late, it's not even valid. Look at what happened here. If we zoom in, see it goes high after this is T2 is falling. If we look at the spec over here, it can go active, and that in the waveform I drew, it's going high when it's active instead of low here. 22 is probably 25 nanos, because everything in here is number 22. Calling number 22. Where are you? 25 nanos. Okay, so here's the deal. I purposely made it longer than the worst case scenario so that I can observe it's still okay. All right? For an IO operation. This wouldn't be okay in a memory operation without a wait state, because as we'll see, if write does not assert itself until after T2 falls, we won't see it until way over here. And then we'll assert we will create our tick signal around T3 instead of TW, which is later than we wanted, but it's okay for an IO cycle. All right. So this scenario is actually probably never going to happen. But let's say it does run that late. The tick signal goes high the first time it sees a low going edge after the write signal is true. And it stays that way until after the next low going edge, which is T3, which is perfectly valid for an IO device. So I got a one that will work and give us what we want for that. If it goes high when it's supposed to, like over here, close to but not after the rising edge of T2. So, right? So here's T1. Here's T2. What am I doing here? These are both late. It looks like the test case is messed up. What am I doing here? I moved the IO rec later. That's what I did. What happens if IO rec goes late early? IO rec is late, but write is super duper late. It's going to give me the same thing I did before because it's the and of these two that logic uses, as you recall. So I'm going to get the same thing. This one over here says, what if it goes high at the normal time, or I should say valid, which is here during the T2 cycle, but before it falls. Then what will happen is the tick will go true on the falling, as a result of, and just after the falling edge, of T2, and stay high during the TW, and then go low after TW passes. And then here would be T3. Now, if you look at the test case and this waveform, you'll also notice that this is super duper long. And so this actually provides double duty in this particular test case. What if there are a bunch of wait states in the CPU? It's configured to just take a super long time during an I/O cycle. And there's many more cycles here because I wanted to make sure that the state logic did not continue to advance and cause my tick signal to go on and off and on and off, which is one of the problems that you can run into if your design isn't done just right. So what we got in conclusion here is the write signal will work for an I/O operation, even if the write signal is asserted by the CPU after the worst case timing is true. It would still work for us, okay? Normally, it'll look more like this, but it won't have the extra timing pulses. So the point is it'll go high after T2 during TW, and it'll give us this ability to see this falling edge on TW and latch our data right there. Okay? Now, if you might argue that this is actually better, and during an I/O cycle, it would be better to grab the data on the falling edge of T3 rather than the falling edge of TW. Yes, you can do that. If you want to do that, just advance your state counter another tick and count up to 3 instead of 2 and assert the tick signal when it equals 2 instead of when I set it equal to 1. All right, so you can move this signal around, is my point, if you want to. I left it clocking early because I want to be able to use the same logic if I want to write to an FPGA resident memory device, if I want to design such a thing. And I don't expect the chip to run at worse than the worst case timing. This is just so late. That's 26 nano, right? So as long as it's less than 25 nanos, and it says, yeah, the worst case is 25 nano, but it's not going to ever take that long. It'll be high, or rather, the write signal will be active before the falling edge of T2, which is what we want it to do, and which it is doing it in this scenario, but it's doing it a little bit later in these other two, okay? So that's the write one. Here's the read jobby. Let's see this one. It's going to work a little differently because we want it to clock earlier than the write. So, in fact, we want it to clock, where do we want it to clock? We want it to clock and look at this falling edge of T2 because remember what we want to do is capture the data that the CPU wants to see and hold it steady in a latch or whatever we're going to do. We want to gate it over to the CPU. And we want it to be stable as soon as possible. Or when we're writing, we want it to go as late as possible. So what we want to do in the reading case is make sure that we, as a peripheral, are submitting a stable signal starting on the falling edge of T2 and hold it as long as these guys are on there, okay? So what I need to do is the same thing, but I want to see it around T2 instead of TW. Now, in the simplest case, you might just say, well, just, go true during state 0. Because during write, we went to state 1, which is this, and logically that must be state 0. Well, yeah, except for one thing. State 0 is over here too. State 0 is always true when we're not even in a cycle. Okay? So we need to rethink the idea of state 0. And the result, what I've come up with, is use state 0 and IOREC is true and read is true. So what happens now is we know that 28 and 9 are both 25 nanos from the falling edge at T1, which means if I AND these two together, incorporating the propagation delay of the AND function and so on, the earliest these two can fall down would be 0 nano after the fall of T1. Worst case would be all the way over here after T2 rises, because that's 25 nanos, right? The worst case. Plus the propagation delay of the AND gate. So the worst case scenario, if I say IOREC is true or active and read is active, would be that I identify that as late is right here in T2. And I want to be able to see a signal that shows me when this falls. So, and because this is not going very fast, this is 50 megahertz, that's nothing. Or 20 megahertz for crying out loud, 50 nanoseconds long. So even if I wait until here, and I have this same idea where I have a signal that goes through here, and then it goes false as a result of this falling edge on T2, that's still going to be 25 nanos long, which is an infinite amount of time, relatively speaking, to the performance of our FPGA, even though it's a simple, slow one. That's more than enough time for it to do its job. So let's look at the logic I chose to do here. I got a single bit state register, because all I got to do now is count from state 0 to state 1. I reset it, I put it to 0, and every time I get a falling edge, I put the state next and the state right. Same thing here. But this is a much simpler next signal, okay? In this scenario, all I need to do is say the next state is true. It becomes 1 if IOREC and read are both active at the same time, and that's what we got down here. Whenever these both go active at the same time, I'm going to say the next state will be 1 after this falling edge. Now my logic will be, if the state is 0, which happens all the time, except for when it's in state 1, which it goes into state 1 when this edge here falls. Okay? Now it's going to stay in state 1 as long as there's a falling edge here and these two are both true. Then it'll get to the point where T1 will fall way over here, and then it'll go back into state 0 way over here in time for the next machine cycle. In other words, on this falling edge of T1 in the next cycle is when our state will end up going back to 0, because state only changes on the falling edges of phi, right? Now it turns out, if we have to go through 2 cycles in a row, we need to make sure our state machine resets itself before it's needed again, right? So let's say there's 2 of these back to back. Technically, the CPU, the Z80 can't do 2 of these back to back. But if we had it set up to do memory transfers instead of I/O requests, it can do memory transfers back to back. So we need to make dang sure that we end up seeing this falling edge without our signals being true. And in a memory transfer, it would be the MREC and read would be the earliest things that are going to happen after the falling edge of T1, because a write, like here, would go true way over here, after the rising edge of T2. So the worst case scenario is we need to make sure that MREC and read true at the same time. This AND function here will always be true after the falling edge of T1 and up to 25 nano, or whatever the value was for 8 and 9. I believe it was 25 nano, which could happen as late as the rise of T2. We already talked about that, okay? So this covers that base as well, just by doing this down here. If I'm in state 0 and IOREC is true and read is true, and again, these are all active high, just like they were in the write logic. So this is basically moving me over to state 0, but I also have to make sure that it's state 0 when I want it to be in state 0. So here's the read variant test case. And we want to see T1, then we want to see the unit on the test here. Sort these to make sense. at least to me anyway. Read, tick, reset, get that out of the way. And zoom out. And what do we got now? We have 2 scenarios for the read test. Resets down there. So here we have the earliest case for IO rec. Here we go. Get that on the screen. View the earliest IO rec will ever become true is right away after the falling edge of T1. The latest it'll ever become true is at or after the rising edge of T2. Okay? Now, the read signal itself generally goes through along with the IO rec, but I didn't do all the combos. I didn't do all 4 test cases because what we really need is to look at the AND function of both of these signals in order to do the test. So the other test cases really are not useful because the state machine is when this and the read are both true at the same time. That's when we clock and advance our states and stuff like that. Okay, so this is the latest and this is the earliest. The 2 scenarios. Now, the read tick is not fully synchronous because read tick goes through when I'm in state 0, and here's the current state down here. It's 0, like I said, all the time, unless it has been ticked. And my IO rec ended with read here is true. Then this is true. That's why it doesn't become true until after here, even though I'm in state 0 over here, right? Okay, now it will go false as soon as I go into state 1, which happens as a result of the state advancing because the state will advance when IO rec and read are both true, and I have a falling edge, which causes this thing to go down right there. And once I become into state 1, every falling edge keeps me into state 1 as long as the IO rec and read are both true, which is the scenario we have here. And the Z80 guarantees it'll stay that way until after T3 falls. So it won't be until here or over here before these things become false, which means that it's the falling edge of this T1 cycle way over here that'll cause the state to finally go back to state 0. All right, and we need to make sure it gets to state 0 before something in this machine cycle over here might want to use it again. And the falling edge of T1 is about as late as we can ever tolerate that happening. Same thing is true for the right. I didn't beat that point, but if you look at the timing, we'll open it up in a second and review that real quick. You'll see it gets reset by the end of T1 of the following cycle for the same reason. So here's this one where it goes as late as possible, which is way over here. And you'll notice that this is smaller. And this is what I was alluding to earlier. This is not fully synchronous. It does not go high as a result of the falling edge of phi. It only goes back to false or low as a result of falling edge of phi. Normally, you don't want to do this in a synchronous circuit design. You want every edge to be moved as a result of the main system clock, because you need to know and guarantee that your setup and hold times are always valid. However, this is breaking the rules a little bit here, because I know that the Z80 guarantees that these things will be true, as I said earlier, by the time T2 is high. So this is as narrow as this pulse is ever going to get, which is 25 nanoseconds wide, which is more than enough for us to do what we want to do here. And that is to identify this falling edge when this is high. And then after that, we want it to go back down to 0. And that's what this state machine does. Okay? This is not perfect, but it's what we want. If I did a fully synchronized thing using phi, then everything would happen so late. It would probably still work, certainly for the I/O case, because we have 3 whole cycles to do it in over here. But in a lot of cases, you don't have that luxury, and you need to get something to identify the situation earlier. So that's why I did this, and why I broke that design guideline. Okay. On the design of my read synchronizer recognizer thingy. Now, let's look at this thing, how I use it in this design. I've made a number of changes. If you followed around the channel when I did this, the speed run port of CPM to the Nouveau board that has this FPGA in it with the Z8S180 chip. I cleaned out some of the doc and notes that said, oh, we don't want to do this, and I deleted all the bad code and all that stuff. I made one or two minor improvements, and I don't think anything was, well, there were some things that were just not too clean in there, and I cleaned it up. You can download this. It's in a separate directory than the Nouveau directory, and you can diff these things to your heart's content and see what all changed. I'll summarize. I added these two signals, and this TP is an output bus from the FPGA to a whole bunch of unused pins on the FPGA eval board, so I can click oscilloscope probes and logic analyzer probes on these signals and see what they look like inside the FPGA. Modulo, whatever, propagation delay the signal has as it leaves the chip, okay? So key is to look at these in relationship to phi. And I also have a scope probe on M1 so that I can orient myself to figure out where each instruction begins and when it's running, so I can figure out where T1 and T2 and so on are on the oscilloscope. As M1 goes true during the first T1 of the first bus transaction of each instruction that's executed. All right, so that'll be handy when we run this. The memory ROM, I talked about that before, and I'm going to just propagate the switch to reset. I should probably debounce this. We'll add that sometime down the road. Now, I redesigned all this in here. Actually, this part of it is not changed. Actually, it's maybe I did a little bit here. Some of these I redefined down below. We'll look at that in a minute. But basically, the short of it is, this is the thing that controls the tri-state driver that drives the data onto the CPU bus when the CPU wants to read from the FPGA. Whenever D out is true, I want to drive data out of the FPGA onto the CPU bus. And the data that, or I said that wrong. Whenever this is true, I want to drive data out onto the CPU bus. And the data that I'm going to drive is coming from this D out signal here, this vector here, okay? And when I'm not driving data onto the bus, I want to tri-state it so that the CPU can drive the bus itself. And D is what I call the 8-bit bus above on the module ports, okay? So this thing has to do with resetting the ROM, the boot ROM. I talked about that last time. This works the same way as it does on the retro board, and that is that when I reset the CPU, I set an RS latch to true, and then when the CPU accesses an I/O port at a known address, I can reset and turn that ROM back off, so I can have what we call a shadow BIOS or a shadow boot ROM type of situation. I talk about that in the Z80 Retro series. Go look at that if you don't follow along. I explain it all in there. This is roughly what the code used to look like. I removed all the begin and all the visual noise in there and cleaned it up by putting defaults in here and then overriding the defaults in this code to kind of compress it down. And when I was looking at it, I'm like, this is just a crummy design for this. This is not the way you want to do this. Bad advice. So I left it in here as a comment so I could talk about it in this video, and then I can delete it and forget all about it. All right? Now, here's the way you want to do this. By default, I'm going to assume that the FPGA is writing to the bus. This is kind of a wonky default, but you'll see why in a minute. The D out by default is I don't care what's on the data bus unless I override it below. This is a parallel case, which means that no more than one of the cases in here can match at the same time. It's a one-hot design, but I might have I'm inventing a new word here, none-hot scenario. Look what happens here and what I deleted in that if then else up here, all right? Let's go back, look at this thing, which is what we call a priority encoder design. And what has to happen in here is the compiler, you have to build a circuit that says if the ROM is enabled, then put the ROM data on the data bus. else, if I'm reading data from this port number F0, put the F0 port data on the data bus, which is how the CPU reads like the SD card bits and stuff like that in this particular design. Now, if you do this, the Verilog compiler has no way to know that I personally am going to guarantee that this or that could be true, but they won't both be true at the same time. Because the logic below, and we'll see that in a minute, is set up in such a way that you can never have the ROM data read logic true at the same time as an I/O port is true. And then the short of it is, it's because in order to read from an I/O port, you have to have I/O rec is true and something. In order to read from the memory, the ROM, mrec has to be true and something in order for that one to be true. These are never true at the same time on a Z80 bus. Well, certainly they're not going to be true. These signals here are never going to be true at the same time because they have all kinds of stuff going on in there. The most fundamental of which is this requires mrec to be true at the same time that an address is valid and a read operation is going blah, 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 blah. All right, so these are never going to be true at the same time. And because of that, I can use a one-hot style design down here. If I don't guarantee that, and the compiler doesn't know that I can guarantee. There's no way to express that when you're using an if-then-else. So what it has to do is it has to build a circuit that says, what happens if both of these are true at the same time? It has to come up with some logic where the ROM takes precedence, that's why they call it a priority encoder, over this guy down here, if that should ever happen. Assuming, of course, the compiler cannot figure that out on its own, and it probably can't, by the way. So if that's not true and that's not true, then I just turn off the dbus out and I set it back to 0 down here. I made it work this way because it matches the parallel case down here. And the reason I set dbus out equals 1 here instead of turn it off and then turn it on in all these cases is because I don't have to say begin and begin. The visual noise down here will become horrific, nightmare, yuck, barf, I don't want to see it, get out of my face. I don't want a priority encoder because I'm guaranteeing that either this is true or that is true or neither of them are true, in which case the default case is true. Okay, so this is not a full case parallel case. This is just a parallel case, okay? This is not full because full would imply that one and only one of these would be true. And I'm not guaranteeing that. I'm guaranteeing that at most one of these is true, okay? Now what happens is by making the default a 1, I don't have to set it to, 1 down here with begin, end, and visually screw this all up. Assume that I'm going to output, and I don't care what's on the bus. By putting it here, I don't have to put it in here, which gets rid of all the begin else down here around the default case. So this is real easy to read, really summarize it, okay? dbus out is 1, and the ROM is on, then set the ROM data over there. If dbus is out as 1 by default, and we've got IO rec F0 is enabled, then send the data from that out. Otherwise, override and shut off the data bus and leave the default garbage on it and go on your merry way. And if you do this, you compile it with and without the old version and this version, look at the results. You can see the number of LUTs used goes down, and the performance can actually go up. And so this is the way you want to do it. And only if you're guaranteeing that at most one of these is true at any given time. And this is really weird to me anyway, because you're saying case 1. And this is because they do allow you, and I think I talk about this in another video, to put your variables down here as the individual case conditions down here, rather than having one condition in here and constants down here. We've turned it on its head. Okay, so each one of these is 1 bit, and if 1 is true, it'll do what it says in here. And if you really think about what this is doing, and if you comment this out and compile it without this, you'll actually see it uses more LUTs. It will be true. I'll leave that as test viewer. Okay? And the reason is, if you think about what this means, without this, what you're doing is you're building a multiplexer, and you have to convert this into, like, address 0 and address 1 to pick one of the n inputs of the mux. With this thing present, you don't have to do that. You can throw away the decoder that's buried inside of the multiplexer and use these single-bit signals to reach into the AND gate that drives that output of each one of the outputs of your mux. I'll leave it as a test to the viewer to go back and review how multiplexers work and what it means to remove the decoder that selects which output, rather I should say, which input is enabled based on the address control inside that mux, okay? And I've got videos on that in my YouTube channel. Just surf around. There's a course I taught at Northern Illinois University called CS463, Computer Architecture and Organization. I talk all about muxes and demuxes and decoders in there. Okay, what else do we got? I deleted a bunch of comments about the PLL. Here is where I use those new finite state machines, and I have these signals called read tick and write tick, and I have two different ones because they have different timing. We just talk about all that fun stuff. I reset it, phi goes in there, and notice I want these active true for these control signals going in, and then the output tick signals are assigned like this, okay? So how do I use that then? This stuff I also kind of cleaned up from before. Here's how I'm now using it. I'm defining these signals because these things were gigantic expressions with all this repeated junk in them. And it was visually difficult for me to see what was going on. So these exist for no other reason for me to say IO-rec read, IO-rec write, which is true when IO-rec is true and read is true. And we just look at all the waveform diagrams, and you can see these are the situations you care about. Memory request is true when I'm reading. Memory request is true when I'm writing, and so on. So I end up with these four signals to control these logic functions down here. And you can see IO-rec read, IO-rec write, read, and so on. Mem-rec or mem-read gets used somewhere right down here. This is when I'm talking to the ROM, the boot ROM. And there's something in here. I'll talk about this in another video because this is going to get too long. But if you want to work ahead, read all the comments in here and play around with these different things. And look what happens when you compile. Each of these statements will accomplish the same thing. And that's kind of funny. Anyway, that's another video. What else is going on here? So I got this thing here. This is a combinational circuit only that's true when the IO-rec signal is true, and I'm reading from this address. And that's in stark contrast to this tick one, which is true during the tick, right? That reduced little window that's only true for one phi cycle. And I'm accessing a port with a specific address, okay? So they're all paired together like this. If I want to write to port number F1, I have this thing that represents the full tenure of the bus cycle, during which time the write signal is true, and so on. And this one here, which is this reduced window size. I don't necessarily use all these things, but I made them consistent because sometimes I want both, and other times I only want one. So in this particular design, I got three different latches. FE is the latch that I use, I mentioned above, that shuts off that shadow ROM. And I want to be able to do that at some point in time. It turns out you could use either one of these for that because synchronizing that particular situation is not critical. But this will be, and this is a video that foreshadows the logic that I want to use. Like I said before, I want to implement a video display controller. It would be nice to, I'm going to make a implementation of one that was real, which is the TI 9118. And that thing has this feature where you continuously write to a port, and it internally clocks and counts all the writes, and that's why we care about these tick clocks. I want to be able to use the otter instruction and spew data into it one after another. Whether I do that or not is actually beside the point. I need to make sure that the implementation of that chip that design in my FPGA will consume data and provide data and get a single clock tick each time an I/O transfer is done. Down here, notice this is a 7-bit address I express in binary, not the full 8-bit like I do above here, because this actually resolves the two ports adjacent. This is port 80 and 81, so look closely. I don't want you to get confused about that. Plus, I got 2 other ports that I've defined in here to read, and I don't know why I'm writing to joystick 4. This makes no sense, and I'm fixing bugs in real time. Always good to do a walkthrough of your own code once in a while, huh? So what do we got here? On port A8 and A9 are the addresses where these 2 joysticks on J3 and J4 are on my Z80 retro board design. Make sure I got all these right. And you need to be able to read these darn things. So, and this is again, currently not used, but they will be in a subsequent video. The reason they're here now is just to show you how I'm going to use these tick signals in conjunction with an address that's decoded. It'll only tick when this address is actually being accessed by the CPU. And this other signal here, which is true for the full duration of the I/O signal. And now when I'm reading in particular, I need to make sure that I'm driving the data bus for the full length of that I/O cycle, okay? Which is why I have these in here. The write is probably not as useful as the read in that context. These these over here are the names you saw above in that one hot mux up here, which will grow as I want to be able to read more and more of the registers. In here, obviously I need to add, what if I'm reading from the VDP? What if I'm reading from a joystick and so on? There'll be more rows in here as time goes on. In subsequent videos, I'll worry about that. But this is how you use, how you read, how you interpret and apply these tick signals is my point, all right? I already talked about this. I'll talk about that in another video. Bottom line is, if the most significant address bits are 0, that's when I'm accessing the low range of memory when the ROM is supposed to be accessed. And there's different ways to do that. Some work better than others in terms of resource consumption. GPIO output latch. Here's me consuming data from the Z80 when it wants to write to me. So here's my write tick. And I'm going to take the data from the CPU and I'm going to write it in the GPIO output latch. Now, do I really need to do this? No. I could just as easily use the write tick signal itself and look at the falling edge of that, or I could use the edge of the actual asynchronous signal, which is what I think I used to do. Which one is it? Is that F1? Whatever, it doesn't matter. I could use this F1 signal and just latch it at the end. As I mentioned earlier, I can run this thing asynchronously if I really wanted to, and it would still be okay. Or I could just repeatedly read the same register over and over again. The problem with repeatedly reading it, of course, is like I said before. What if the peripheral counts or something like that? So that's why this is in here, just to test the above design on the actual circuit. And the same is true about this over here, the SD signals. Yeah, if I'm reading from the SD card, I could use a regular buffer. It doesn't even have to be latched. And on the Z80 retro board, it's not latched. And in the last version of the Nouveau, this is simply assigned. The data is simply assigned this without it being synchronously latched or anything. I did this in this particular code because I want to run it in a real circuit just like this up there so that I know that the logic is working correctly. And everything else down here is the same as it always was, okay? So let's go ahead and compile it up. And looking up here, it's nice to know I could run it as fast as 144 megahertz of the current design if I want to, even though I'm running it at 18. Okay, I do make prog, and I'll write it over to my board and my Raspberry Pi programmer thingy. Here's the screen of the CPM console of that device. If I hit reset, and it boots up. If I get here, I know everything is working, as if you look at the previous videos on how all this stuff works. In order to get here, it has to access the SD card, which means it has to read it. It has to be able to write to these two latches we just looked at. Namely, this F1 and the F0, these two guys are reading and writing to the SD card through these latches. And if I didn't do it right, it couldn't read it. It would not get this far by a mile. All right, and we can do the adventure game, and everything's working fine. Blah, 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 blah. Okay? So in order to see that this thing actually works correctly, we need to write a piece of code that actually performs I/O operations that we can recognize on a logic analyzer or a scope. And I got DDT here, which uses 8080 mnemonic, so I'm going to say assemble at address 100. I'm going to read from port 80, because that was one of the decoding ones that would be used in the future for the VDP. And I'm going to output to 81. Then I'm going to jump back to 100 and spin in a loop. L100, disassemble, show me the code, make sure I typed it in right and it recognizes it okay. So he's going to read from port 80 out to 81 and then spin like crazy. If I do this, now if I go over to the scope and I grab a picture, we see this. Now, what I've got here is this is the write tick, the read tick, phi, and M1. So here's the jump, because it's not doing any I/O. Here's the in with the read. Here's the write, or the out, with the write tick going off here. Now this is set to mark T1 in the write cycle. Let's put this aside a moment. Have a look-see at the documentation of the Z8S180 and find mass confusion setting in here. In order for an input operation to take place, we have a 2-byte instruction. So this is how many bytes the instruction, how many machine cycles there are, and how many T-states for the whole thing. Okay? This is just wrong. Can't be true. It's got 2 bytes. It has 3 cycles. It's going to read opcode. It's going to read the 1-byte operand, and then allegedly do an I/O operation in 3 more T-states. When all I/O operations have a mandatory wait state in there, this has to be 10. This is just wrong, okay? And we'll see that in a second. Now, an output instruction, it's supposed to be alphabetical, I guess. What do they say about that? Out. Outie, out M. This one's supposed to be 10. Okay, and it is 4 machine cycles instead of 3. I submit that it will have 11. Okay, so this is just wrong. Okay, so be careful. The out will take 1 extra clock to turn around the bus inside the CPU, I guess. So the out does take longer than the in, and you'll see that here on the scope. And there's no arguing here when you see it on the scope. Now, my FPGA code might be wrong, but the phi clock and the M1 from the CPU don't lie. So let's look very closely at what's going on here. And we will succeed in spite of their bad documentation. This does actually exactly what the doc says in this part of the doc that we were looking at before. When they give you the timing tables, these cycles work like this. Okay, I/O operations take 4, and the regular bus memory operations take 3, because I don't have a wait state in here. But there's one T1 state that's not shown here, which is an internal cycle that the Z80S180 will take when doing an out instruction, and you'll see it in here. So let's look at the input instruction first. Or rather, I said that backwards. Let's look at this one first, which is doing a write, and which is an output instruction. Okay, so let's zoom in a little bit. It's M1, that's phi, that's the read tick, and that's the write tick. So I'm going to use the manual as a straight edge. It would be nice if I took the picture in the right It's a little crooked, isn't it? Kind of hard for me to turn this window a few degrees. I apologize for that. We can still sort of see what's going on, though. What do we got here? M1 goes true, and there's T1. T2, T3 to read its opcode. And this is an out instruction, so it has to read the immediate operand, 1, 2, 3 cycles for that. There's an extra T state right here that it uses internally as part of the instruction. So far that is 7 T states. And then we've got the 4 T states over here to do the I.O. cycle. Here's T1, here's T2, and you can see that this thing goes true on the leading edge of T2. Is that? No, it's on the falling edge of T2 because this darn thing's crooked. And then it goes back down on the falling edge of the wait state here. Here's T3, and you can see down here, there's the next instruction. So this is a total of 4 plus 1 plus 3 plus 3, which is 11 total T states, not 10, okay? And you're going to see the same thing is also wrong about the input instruction will be off by 1 as well. So whoever documented that did it wrong. Here is the what's this one? This one is the input instruction. So you're going to see the same sort of a thing. You got M1 here, so you got 1, 2, 3, reads its operation, the immediate operand, 1, 2, 3. This here is easy to track up because this is going to be T1 over here. And this is going to be T2, and you see this thing is not quite as wide as this one, right? Because remember, this is the one that starts when it starts, but it ends on the falling edge of the wait state here. I said that wrong. It ends on the falling edge of T2 here. Here's the wait state. Here's T3, and the CPU is going to finish its read operation on the falling edge of T3 here. So the read gets done here on this falling edge 1 phi clock earlier than the write, which does it over here at the end of the wait state before T3. Optimally, this would be done over here on the falling edge of T3, except if I wanted to use this same decoder, like I said, during memory transactions, they don't have as many cycles, and I have to do it on the 3rd clock instead of the 4th one in the total sequence of the machine time states. All right, so that's the whole ball game. I wanted to make sure that everybody saw this, because if we want to build a synchronous peripheral and hook it up to a Z8S180, we are going to need a way to do this and this and pick the specific edge that we care about out of the morass of edges flying around when the instructions run. All right, so let me know what you think. Thanks for watching. I'll see you next time.